Hi mates, so I've never been playing Minecraft on my own, but I knew that people even managed to make computers and the CPUs in Minecraft using what is known as redstones and torches as well. So I never had a look, closed or detailed look at how this works until now, and quite interestingly that you can implement some very basic logic, let's say, that allows you to build the entire computer. So you start with some very tiny building blocks, some a few of those. So literally we're supposed to be using just one of them, like the NOT gate, logic NOT gate. And with only those basic elements, we can build something up to the entire computer, that like how someone has made an entire Minecraft that is running without the Minecraft, just with these redstones, like very basic building blocks. So the idea is that they just can build the emulator, the simulator of the real hardware. So it's not the emulator like we can write like 6502 CPU emulator or something like. It's the real hardware level emulation, like not the transistor level, but the logic gate level, I would say. So it's even lower than writing in I don't know, machine codes. So it's literally like you could have do the same with the like soldering the PCB or something, but without need to like the hardware. But if you just pull out the electricity and circuitry from there, because I don't quite understand how that thing works, and the only thing I do understand is this binary logic, which I'm really fond of and fascinated by. So I really want to take that and have it separated. Now, a few words in regards how this works in Minecraft. So you just better watch the videos like, for instance, this one, computer logic gates in Minecraft with only redstones and torches. So just so here in this video, the guy creates like AND gate, OR gate, NOR, XOR, and many more. And he uses this two very basic elements, so like just the switch and the inverter, and he uses some like lights or diodes, you can think of them as diodes, to like see if the signal is working. And what is interesting, so there are many simulators that allow you to draw the binary logic if you have some backgrounds with electricity, some electricity backgrounds, like that sort of a thing. In that case, you might find those really like good and comfortable to use. Yeah, really, literally just comfortable. Because when I've showed this implementation to my dad, he said that that's just sort of a mess, and he doesn't understand like why someone has come up with such a weird way to represent this sort of a thing. But for me personally, as for the guy who has no idea about how the electrical part works, I find this quite pretty fascinating. And since people has been using within Minecraft for years, and they will build the entire computer, like not only the CPU but also the memory, the display, like everything. This is a display here, so there are also some memory blocks, the CPU itself. So it's really complicated to say the least. So this actually proves that this method of representation, the composition of the binary logic elements in the Minecraft way, actually makes sense and works, and being used by I believe thousands of people so far, like before. So it makes sense to take this logic from the game. I made some minor changes because, well, in the game it's 3D and it has like a little bit differences because it's in 3D. But generally, I tried to take the very concept from how this works in Minecraft, and then just get rid of the entire Minecraft and just end up with having these this binary logic like elements, let's say. So I will now show you what are we supposed to be developing in this video in particular. So if you have a look at the source code, so I will be partially writing this, partially copy pasting like some constants, for instance, just to avoid this video lasting forever. So I would rather take more time to explain things rather than type. So this is the entire source code, like 200 lines of code, a single file, and you come up with this sort of an application. So you have the switch, button, inverter, wire, light, then the raise tool, and well, single step and is not currently working. I was just using this for debugging, but I'm not quite sure whether we're supposed to be using this or not. Probably we do. Well, we'll see. I'm not sure. And operate to change from the built-in mode to the mode where you can actually like turn on the switch or something like that. So just to demonstrate you very quickly how this thing is supposed to be working. So let's kickstart with the wires. So the dark green wire represents that there is no signal, like the current is not flowing within the wire. And for instance, we can put the light and we can even make it bigger so that it just makes sense in terms of like have a bigger light if you want. And let's put a switch here. Now I go to the operate mode, and if I turn the switch on, the signal goes, so it shows like this wire starts being like light green, which tells that the current is flowing, kind of flowing in here, and then it lights up the light or diode, call it however you want. So that's how it works. And now for instance, so this is the first thing that we can do, just the switch. Then let's say we take an inverter and put this inverter, first put it in here. So this purple thing is an inverter. And you see like it already works. So since we had no, just even to show this a bit in a bit more detail. So I just want to put a wire back in here. Okay. So if I just put the inverter separately like this, it's not activated. So in order to activate it, we need to here to put either logical 1 or logical 0. So for instance, if I take a wire here, then it just activates because here we have the 0. So this guy activates, inverter activates like this. And if we put some wires on top, they get activated as well. And let's say put some light here as well, for instance, like so. They also get activated. Okay, so now if we put another switch in here and go into operating mode. So if I activate the switch, then these two wires making like giving an input. So we have the input from the bottom and the output on top. So once we have a logical 1 as an input to this inverter, or you can think of this as the logical NOT gate. So it comes in, and then when it comes in, it just turns off. So the signal inverts. So we have 1 in and we have 0 out. Now, if we swap this back, so here we now have 0 in, hence we are having like 1 out. So you might be wondering like it's not really electrical, but that's exactly how it works in Minecraft, and I personally find it really fascinating. So this inverter at some point it works as the power supply as well as the switch, which doesn't make any sense from the electrical perspective, but from the logical one, especially if you have no backgrounds in like electronics, this might be really kind of easier to play around with and to build something with this sort of things. So these two basic elements are already enough to build an entire computer, believe it or not. So that's what is claimed in this video in particular, where Gaga does exactly these two elements, but using the Minecraft blocks. So here we have exactly the same thing, but we have this like flattened, it's only 2D, but again, for the sake of like clarity, simplicity, and since we're not interested in playing Minecraft here, but just to build computers, let's say, this should be fairly enough. And it has another feature which wasn't intended initially, but yeah, so just to give you an idea, so we can also delay the signals a little bit the following. So if we only have one square in between, and we put a switch here, and for instance, I also put inverter in here. Okay. All right. So you just notice that the speed is a bit different. So this operates like this, 1, 2, 3, and again, 1, 2, 3. Okay, and this one operates like 1, 2. Okay, and again, 1, 2. So if, for instance, you're building a generator or a clock, that may be used the following way. So we can consider two types of clocks. So, for instance, we have inverters like this, really close, and if we have them like this should be fairly, yes, better. Oh, sorry, put them in here. So now take the wire. So I don't close for now. So taking the wires like this, and okay. All right, and also here. So I would now activate both of them. So first we start with this one, and it so you see the frequencies like this, right? But in here we'll have the frequency that is supposed to be a bit like slower. So just see nicely that this one is operating faster as opposed to this one. So this is how it's working. So this might be used for some purposes, let's say. There is somewhat a similar thing in Minecraft. I'm not quite sure, don't remember exactly how that is called in Minecraft, but there is a logic to delay the signal. So here it's way more simplified as opposed to how it's made in Minecraft, but for now, as far as I'm just trying to play around with this could be fairly enough for now. So in order to build, let's say, 1 bit of memory where you can store data, you need a whole lot of space. I guess it involves many logic gates, and just to give you an idea, so I just try to build some simple AND and OR gate. So like for instance, here we have and let's put the lights. So these are the inputs. So 0 and 0 results in 0. Now 0 and so bitwise AND operation. So we take the wire. So 0 and 0 results in 0. This is turned off. 0 and 1 results in 0. Now 0 and 1 like this also results in 0. But if we say like 1 and 1, so literally this and this. Oh, I forgot to. So yes, so 1 and 1 equals to 1. Now if we get rid of either this, it doesn't work, or both, it also doesn't work, or like this, it also doesn't work. So it only needs this and this to be equal to 1. In that case, it works. With OR, you can do, yeah, so just, I need to turn this on first. So here, for instance, if we take wire, so if we take either this, well, like this wire is also, like, current goes here as well, so it works in this way. It also works in this way, yes, and it also works in this way as well. So this is the OR element and this is the AND element. So just to bring them to the initial states to give you an idea. So with input zeros for both cases. So also you can do XOR, NOR, and whatever element, logical element you can imagine. Then you can combine them together to build memory, to build registers, to build like comparators, like I don't know, binary adders, whatever you want to build. This can be built. Here we are encountering the second problem. So if we want to scale this, so say I want to have like at least 1000 by 1000 squares. Currently this has been implemented using the HTML table, which is quite laggy, but it's incredibly simple to work with. So I'm using this for debugging purposes only. So the second version that I probably would make a tutorial on that as well would be involving like probably the HTML canvas element. So we're going to be rendering this, and I'm not quite sure how you can click on the canvas to get the output. So then research that, but that should be fairly simple, hopefully. So then the second version would be improved so that it can be scaled even more, because canvas doesn't take that much of memory, so it can be like literally like as big as we want it to be, because to make something really huge like a CPU or a computer, it needs to be really big. So I hope that makes sense. And now, without further ado, let's actually build this kind of simple application. So I'm sorry for the intro, it kind of took too long. And I'll try not wasting your time with typing too much, so I would be partially reusing things like the constants here and things like that. But anyway, so let me just start with a bit of copy pasting, because there's nothing interesting is going on here really. So if I just open up, nope, not this one, view folder. So I'm creating, I don't even need HTML to be honest here. I don't really need it. So I'm having these two divs, so the board div and the tool div. So let's, and this is not going to be working for now because we don't quite have these functions, so I'm not quite sure if this is ever to be like, so probably if I just command these out, this should be just fine, yeah. And yes, this one. Okay, so we don't yet have, and so if I just inspect the elements here, so we don't yet have the board, obviously, because that would be generated by the JavaScript. So we have div board, which is empty for now, and div with tools, which kind of uses, so it's using the table as well. As I know it's horrible. I just wanted to make this as quick as possible, so that's my layout. It's not obvious to make it this exact way. All right, and then the entire logic is going to be happening within the script tag, obviously. So I just start with grabbing the constants. Yes, so probably board, yes, and tools to operate, and also there is one more which is responsible for these guys. Yes, just I don't have all the variables in one single place for now, but now I will. So just to give you an idea what these guys are all about, so let's make sure no errors, nope. Okay, so just for the sake of clarity, I'm using these constants to name the tools. So we're supposed to be having, so we're having the tool variable is very essential. So this variable is tool. And once we click on the button of whatever button in here, this tool variable gets the corresponding value. So for instance, if I just to give you an idea, so here I just want to say what the tool now equals to 0. So if I say switch and now tool equals to 1, if I click on button, now tool equals to 2, and so on. So we don't quite need step here. So I can probably even just get rid of the, I don't need this step for now. We could have no, probably we don't need this. Like in the eventual version, when I make the proper layout, maybe this would be available, but for now doesn't not need it really. So for instance like this, and erase 7, yeah. So this is how it works. I'm not quite sure where the 6 goes. So 6, oh, for some reason Yeah, there was something for 6, but I don't know where did I lost the 6. Arrays could easily be 6, but should I really do I have any 6 in here? I don't. Well, I think nothing can. Yes, I can probably make it 6. So off board, we'll talk about this a bit later. So powered is just a bit that we're going to be, in order to power up or power down, we're going to be bitwise ending with the bit 32. And also marked is when we're supposed to be traversing recursively our wires to make sure the signal reaches the certain point. We're supposed to be using the 64th bit. And also this value tool, like the first 4 bits, the bitwise end whatever we have the board on a given square, to make sure that we strip the all the bits like powered and marked, so to restore the board state back. So this I would be explaining this by the time of implementing some logic, basically. Okay, so what else? So board is the internal representation. So this is going to be an array. Size is width multiplied by height. So this can be variable later on. I would probably add some text fields, text inputs to make like user defined size for this. But for now, it just can be altered from the source code. So then the traversed is the array that is supposed to be used while we're traversing the circuitry, to make sure which squares, like which wires or lights or whatever elements that can be turned on, right, and being traversed, that would be specified in the function below later. So we want to make sure that we store all the squares there, and is powered is also the variable to the helper variable that helps to helping the routine that is supposed to be like do 2 things, like literally restoring the board by clearing these marked squares and powering up those elements that do hit the power supply. So power supplies in this particular implementation, so inverter is also power supply, as well as the wire. No, wire is not, light is not. So inverter, button and switch. So button works just like in Minecraft. So you just switch, it gives power for a couple of seconds, then it drops back. So it would now be much easier, hopefully, to understand. So yeah, let's kickstart with the initializing the board. So the first thing to do, so function init board. So what we need to do here, we need to loop over the rows and the columns of our board. So equals to 0, row is less than height, and row plus plus, and the same for the column. Okay. And so here is the formula to calculate the current square. So we need to say row multiplied by the board width plus the column. And we take our board indexed by the square. This is going to be equal to, I guess, 0 or empty. I'm not quite sure. So yeah, 0, but yes, empty. So we have this. So this is going to be equal to empty, which is 0. And also we need to initialize the off-board squares, because the recursive algorithm might hit the edge of the board, so it should no longer be wrapping around, because we just mess up everything. So here is the condition. So if we have the column 0 or column width -1, so like, okay, just probably we just leave this for now. We just leave this for now, and let's just call the init board. So we can't see the result yet. So to see the result, let's implement another function, which is render board. So function render board. And here we do a very similar thing. Okay, so also looping over rows and columns, but here is a little bit different. And so we are supposed to be, so let's create the board HTML variable. So it would contain the table and cell spacing equals to 0. What else did I? Yes, pretty much all. And by the end, I want to say board HTML plus equals, and we just close the table tag. Now we need to find our board, so document.get element by ID, and here we are looking for our board, this one, so board, and in HTML is going to be equal to board HTML. And now it probably doesn't render anything yet, but at very least now, yeah, that's because, hold on a sec, board, oh, because I just didn't call it yet, surely. So render board. So now, although it doesn't render anything, but it just creates the table. So now we're going to be populating this. So every row we need to say, oh no, it's not here, the wrong function, I'm sorry. So in here, board HTML plus equals, and we're taking the table row, and that's, I guess, it. And we say board HTML plus equals, and we are closing now this tr tag. So let's make sure that is the case. Yeah, it creates table body automatically for us. We could have added this, but I don't see pretty much any reason for doing that. So now, for instance, so here we can say like board HTML plus equals and table data and just some random value, or we can even put the value of board square and plus td like this. So whatever values we now have are being displayed. So for instance, if within our init, instead of empty, we do some other thing, it just prints, it should be printing, okay, it doesn't for some reason. So we want to init the board square. This is a bit strange. So why doesn't board square? Yeah. Oh, copy paste is a bad thing. So this line was actually erasing everything. Yeah. So yeah. So whatever we do, like for our initial representation, like whatever we have here. But now we also need the address of the board to be initialized with the off-board value. So let's go for this. So here I just drop back to empty, and here I say if, for instance, call is equal to 0 or call is equal to width -1. I want to say board square is equal to off-board. So now you see like this 8 stands for the off-board. And also another thing, so also if row is equal to 0 or row is equal to height -1. So now it should draw here on top and here on bottom as well. And it does. And now what we can do, so for instance we make this like 20 by 34 and this should draw like the corresponding. Okay, so the problem here, so I just messed up with something. Let's check this. Okay, because I use height both cases, obviously here should be the width as well as here. Okay, so yeah, now we have it like this. Let's make a few more tests. So let's say width is going to be 10 and height is going to be like 5. Okay, 1 2 3 4 5 6 7 8 9 10. 1 2 3 4 5. Yeah, so now this makes sense. So now we can, by altering these width and height, so let's drop back to 13, we can actually do this however we want. We can change the board size. Okay, but obviously we need to want to render the squares and here, so I have this render element. So yeah, I just guys, I just take this board HTML from here, so just copy, and so instead of doing just printing this board square, we would add some attributes in here. So what happens? So well, ID, I'm not quite sure whether we really need the ID, maybe for, yeah, probably. No, we actually need, because to handle the on-click events, yeah, we need the ID to pass like which square how did we click on. So this ID, it makes sense. Then the border, just no border, 0 pixels. Width and height like 40 pixels, just for proof of concept testing purposes. And on click, that would be the click square, which doesn't exist now. So we just get rid of it for now and just say alert and this .id, so to check whether the function works and what the ID, and the render element doesn't exist yet, so function render element, it takes probably the square as a parameter. Okay, so it takes the square. All right, so now whoa, it's undefined. Oh, well, that's because this should be returning. Let's just return nothing for now. Yes, so it just, well, let's for instance say return just div style. Just I'll use another one. So background color. Say gray. Okay, still doesn't work. Width and height should be also specified in here. Height. Yeah, so now we allow, just to give you an idea, so every table row has the table data, and within the table data here we have our div with width and height equals to 100% and background color gray. But we need to draw some different colors depending on the content of what we're supposed to be having on our board. So we can have like empty squares or this operator switch or whatever. So now already I think that we can actually, like, let's put one in here. Oh, it's it doesn't do anything yet, so yeah, so on click just, yeah, but at very least we can see, we can kind of inspect these squares. So yeah, just the square number so far. So yeah, let's probably keep going with this render element. So depending on the element that we are having in here, so just quickly grab this code because nothing really, no rocket science in here. So what do we have here? We have just the render value, the render variable, which is string, and eventually it would take one of these values and get return after. And then we have the switch statement that takes the board square, board index by square as an argument. And also I need to make sure that board square gets into the parse integer, render element and square. Hold on a sec. Oh, it is integer here because, yeah, we compose it from integers. Yeah, so this is going to be a disaster when it comes to like the click square function. So depending on what we have on the board indexed by the square, we can have either the empty, the switch, the button, and so on. So far, all those we are supposed to be recognizing are the off board, which is this one, and also we have like the empty. So now this should be rendered differently. So the off board squares should be rendered differently, and indeed they do. We will later take this away because we're not interested in observing those. So, so the line that does this. So exactly the same line that we've been using in the init board in here. Is this the same? Yeah, it is the same. So if we encounter this exact squares, in that case, we just do not want to continue, and we just drop. So now we no longer have these. So how about drawing things on the board? We need to make our click square, actually put in the element whatever we have. So far, say I click on switch, and the tool variable holds the value 1, which is the code for switch. But when I click, it doesn't put a switch on because the click square is not working for now. So where is my click square? So yeah, here is a very simple routine. Where is my click square? I don't yet have the click square, do I? Yes, I don't. So click square, yeah, here it is. So it takes two arguments. The first one is the ID of the square we have just clicked on, and also, well, the tool. Hold on a sec. I don't really need to send this tool because, yes, I don't need to send it because tool is the global variable. Indeed, yeah. So far, so good. So, yeah, I think this should be fairly enough. So what it does. So in case if tool is equal to operate, we do not want to draw anything on the board and we just return, because in that case we would be able to use like pressing the button or toggling the switch, the checkbox in our case. So otherwise we might have an erase tool. In this case, so this is another special case. We don't want to do anything but just whatever we have at the board indexed by the square. That we taken from oh, hold on a sec, did I click square? Where is my, okay, I just forgot function click square, forgot to make a function, so it takes the square, that's it. So if the tool is equal to erase, we just set 0. I actually may say this empty. Empty. And otherwise, whatever our tool equals to, we just put this on board. And after we print, I believe we need to print the board anyway by the end. So that it would get updated later, but when we put something on board, we want this to be re-rendered from scratch. Okay, so let's give it a try. So switch, print board is not defined. Okay, now because I've changed the name to print, oh, so actually the render board, not a print board, but the render board. So let's put a switch, and we do have a switch. Now, if I try to toggle, it doesn't work. So I go to operate, and now I can toggle my switch on and off. Same with the button. So I put the button in, and only if I operate, I can click on it. The inverter, it's not powered up, so it's not actually activated for now. So just like inactive state, as well as the wire, also inactive state, and the lights also inactive state. And if we want to erase, we can actually do that as well. So we can erase everything. Yeah, so this is it in regards to the user input. So this is that simple. And the next thing we want to do is like the heart of the entire program. There is the function called update. No, it's update board. Do I ever use the update board? Hold on a sec. Update board. I didn't even use it. Oh, update state. So I don't even need to update board. Yeah, just some gibberish I forgot to get rid of. Okay. So it's always good to make a tutorial after you've written some code, because yeah, just okay. Update state. What it does? Yeah, traces the signal for all this. Yeah. So we'll come up with this a bit later. And this is the main loop. Okay, so trace signal. Yeah, trace signal is the core function in here. So yeah, here is the function, the trace signal. So yeah, I'll probably just grab this, because if I this is the function I spend the most time on implementing it. Yeah, just if you make a tiny little mistake, the entire logic is not going to be working. So just to make sure everything is fine. So let's walk through this. So you may, for now, yeah, I'll probably just comment out those things we are not interested in. Just can get rid of this for now. So and where the trace signal is called from. It's not called for now. So yeah, let's probably, yes, the way I've been debugging. So for the click square in the operate mode, just for debugging purposes for now. So here, this is just for debugging purposes, guys. You do not need to do this. Well, if you're following the tutorial, you can, but so trace signal. Okay, and the square, yes, trace signal takes the square and also the direction as well. Square, so direction might be like, I don't know, some random value, -100, I believe I've been using this. Just like the value that can be like the initial, because we just need to put some. We can actually even ignore this. It would be just undefined in that case. That probably should be, yeah, click square, and we just pass the square we're clicking on. Okay, so we are now supposed to be debugging this, and let's get rid of this as well. So just to make sure, so just alert trace signal. So just want to make sure that it is alive indeed. So let's draw some wires and operate and whatever trace signal. Okay, and actually it should be here as well. Okay, so that's how we're supposed to be debugging our trace signal then. So the core logic is here. So here is the list of those particular elements that we're supposed to be tracing. So these are the following. So if tool is equal to either wire, light, inverter, the powered inverter, powered wire, or the powered light, in this exact case, we are marking the square, the board index by that square, where the function is currently at. So whatever it takes as an input. We turn on the 64th bit, which is this marked. So the marked is the 64th bit, just to make sure that we have already traversed that. So that's a sort of a pathfinding algorithm at some point. And then we push in the square into the traversed, which is here. So just a list array. We can push values there. We would then just like pop the values from there, and this is powered is no longer on the cards. It's not on the cards yet, but we'll get into it a bit later. And then, so this is the core, this is the heart of the entire algorithm. So we then just call the trace signal recursively. +1 is one step to the right, -1 one step to the left, plus width one step, I think down, yes, and square minus width is one step up. And since we will need to know the previous direction of where the function was at, we also need to make sure that we pass the direction as the second argument. So when we call the function for the first time ever, like for instance in here, so we're just not specifying the second one, which would make it undefined. That's the nature of JavaScript. But when we're recursively doing this, the previous direction would be stored as the second argument. So every time we are recursively coming to this trace signal function, we would already know from which direction did it come from, which is important for implementing the inverter, so that we make sure that it has the output on the top of the inverter and the input in the bottom of it. So hopefully that makes sense. So far, I don't think it would be doing much. I just need to, so what was it doing in, so restore board, no, update, yeah, so traverse signal, yes, and then the restore board. So yeah, we need to add the restore board here as well. So again, just for testing purposes for now, so we'll get rid of this later. So here, just restore board. So we don't yet have this function, but and probably restore board is not really the proper name, because although it does restore the board, that's my poor practices of programming. It does restore the board here. Like it just gets rid of the marked bit. So when we've calculated all of the squares, just make sure the values are like drop back to the initial like values. But also the main thing it does, it actually gets, so it's power up. Powers up if its powered is true, and if it's not, it just powers down the entire set of squares that are available within our traversed array here. Where is it? Where is my traversed array? Oh, it's not here. Within the traversed array in here, this one. So I'm just thinking what would be the better way. Yes, probably just drop in the I don't want to call this restore board, so probably manage power is the proper way for this. So let's put it in, but I just want to call it manage power or update power. Probably update power is the proper name. So trace signal and then update power. But so far still nothing is going to happen because we'll now quickly walk through this one, but it relies on the isPower variable, which is not activated so far. So if we do not touch our inverter, but just be working with this the switch, either powered or not, and the button, yes, so they are the sources, they are the power sources, power supplies in some sort. So the idea is following. So yeah, I get rid of this for now as well. So just to give you an idea. So let's say we have some circuit here. So the wire goes like somehow, we have some lights here and here, and we have a switch in here. So if I turn this on, you see like nothing happens, right? If I turn it off, nothing happens as well. Well, that's because, when it encounters a switch, it should take an action. So this is what this piece of code is doing. So while the recursive call, if we are hitting this switch, which is powered, or the button, which is also powered, and by the way, I'm not quite sure. Yeah, there was logic somewhere to make how to make the button being powered, but for now let's just stick to the switch. So if it encounters the powered switch, then it should turn this isPowered variable to on. So update power. If it's powered, so it traverses all the squares within the traversed list, and by default it does strip all the bits, like the marked bits, and if any power bits as well, it just strips them also, strips everything but the value of the element. Now when it's powered, and if it's not an inverter, either just the turn off or the turn on, in that case it just makes it powered like this. And hold on a sec, do I really still? Yeah, so this actually ensures that the inverter is not treated as, I don't quite remember if we really need this part. I'm sorry guys, I just don't remember if we need this part or not. I didn't yet make that the way I develop software, which is really weird, doesn't involve those. Okay, anyway, at least now this is the working version, so we don't need this, and definitely we don't need this. And by the time of the update power, it erases the traverse and the isPowered variable is set to 0. Okay, so update power, so now it should be here. Yeah, so if I did everything properly, this should now be able to, so let's put some small wire, put a switch, and whoa, nothing happens. So 84, okay, it goes somewhere horribly wrong. Oh, that's weird. Oh, the pass in, yeah, this is it. So trace signal, this is I ran into this pitfall again. So square is a string, but we need to convert this to integer to make sure it works properly. Oh, what a noob I am. So in here, so obviously, so parse int. So the problem is that this square is actually a string, like the ID for this, for whatever element we have, like is string. You see, it's not an integer. We could have changed this, but yes, let it be like it is now. So now this should be working, hopefully. Console switch operate. So yeah, now it doesn't run away, and now I probably should also render the board to update it manually. Yes, so after I've rendered the board, you see like it gets light up because it is connected to switch. So now it's not really that like comfortable to do, not handy to do this like manually calling this render board. So, and since in this case, let's say we have like 2 of those. So if say we have more than one group. So let's say we have 2 groups like this, and I have 2 switches as well. So, and I just click on one of those and then render the board. You see like the second one wasn't like updated, but it should be, so I need to click this again, and it's not really that handy. So ultimately there may be really lots of groups like this that are not separated with each other. So what we need to do, we need to traverse every square, and for every one we need to call this trace signal thing. So here is where the update state function is getting really handy. And so we are no longer doing this in here. So here we just, when we operate, we just return, so like it was before. But in here, so update state, so we're looping over all of the board squares and calling the trace signals for every square. And here we can have, instead of having the null, well, yeah, we can have null, we cannot specify anything that would be undefined in that case. So that's the direction, the initial direction value for the trace signal, this one, which is not going to be used for now anyway. So hopefully that makes sense. Yeah, we don't want this part of code. So I'm going to be explaining this a bit later. And also to make, so now we are coming to introducing quite an important feature that is available in Minecraft as well. So that's known as ticks. So the idea that in Minecraft everything gets updated during the game ticks, and that's somewhere around 20 ticks per second, if I'm not mistaken. So now for debugging purposes, I'm using this set interval function. So what it does, so after we have initially done all this things, we can probably, yes, so it's still fine. So here, render board, render board. I'm not sure if I need to render the board initially. So this would be doing like traversal, like going over all of the board squares and calling this trace signal. And it's not the restore board, it's called update power now, update power. So traversing every single piece and updating the power for it. So let's see if this now works. Okay, so it just happens after one. If I don't do this initially, it just happens after the delay, which is acceptable. Yes, which is acceptable. So yeah, yeah, I don't like it. Sorry, I just don't like it. It's a bit of duplication, but yes, at least. So now if we just take some wires, so we have like 2 groups or even 3 groups randomly selected somewhere. Now we take a couple of switches and we operate. Then you see like it kind of works, whatever we have. Now if I put the wire in here, see like it updates, and if I start adding some wires, it just gets updated as well. So this is the very basic functionality. Now one last thing before we proceed. No, probably it's not been. So what it does here. Yeah, so actually this code is important because it prevents, so this condition prevents from powering up. So yeah, within this block, what do we do here? We either power up or power down our elements like wires and lights, and probably, I'm not quite sure whether it spreads onto switches and buttons or not. It's not really important. But when it comes to inverters, since we need to invert the signal, the matter of handling the powered up state, the powered state of the inverter, this happens separately in here. So let's do a couple more tests. So if I just take the inverter, for instance, and I put some wires, and let's say put a switch in here and operate. So you see, like, it just ignores the inverter. So when it hits the inverter, it just like passes the signal through. So in order to avoid this kind of scenario, this part of code is actually what we need. So let's uncomment this one first. So in case if we do encounter an inverter, like not the powered inverter like in here, but just the turned off inverter, in this case we just should drop the signal. The signal is not going anywhere else, so hence the return statement. But if the direction, so here we define the input to the inverter. So if this comes from bottom, so not from here, not from here, not from here, but exactly from bottom, in that case, what happens? We need to manually, so baud square in this particular case, the baud square is inverter indeed. We do manually power the inverter. So it's really weird. It probably might be implemented much better, but that's code monkey king's way. So all of the elements are getting powered or like turned on or turned off, like here turn on, here turn off in the update power function. But inverter is special, so it gets updated within the trace signal because it needs to implement this logic of actually inverting the signal. So by now it should already not passing the signal through itself. So if let's start with the inverter. So if I now put the wire in here, since the input to the inverter is 0, so it's not powered up, it actually gets activated. So you see, like, it lights up. But for now, if I put some more, it doesn't do anything because we don't yet handle the case when the trace signal loop encounters the powered up inverter. So let's get this one as well. So in case if we do encounter this power up inverter that is powered up, okay, in this case it's quite similar. So the first thing we need to make sure, so if the direction, so this line, so let's probably just get rid of this for now. So just to show you all of the functionality that we need, at least conceptually. So we put an inverter here and we have some wire. So now this wire, since it's logical 0 as an input, so down below we have an input to the inverter. So the input is 0, so this is not light up, not powered up. So it just turns on. But in order to turn this off, if we just take a switch and we put a power in here, so this input now turns into 1, logical 1, hence the inverter is turning off. But still, it doesn't produce any output, so it kind of doesn't work as a power supply, power source for now. So if, say, for instance, I toggle this, I can toggle the inverter itself, but it doesn't yet affect the output. So here, this line of code, what we do, so if direction is like the top side, the upside of the inverter, so this is direction is equal to width, and if so this additional one, like baud square minus direction, so if anything is powered and not a 0, or is it? Yes, it's just as if there is anything powered. In that case, we have, so hold on a sec, let me just make sure I don't mess up anywhere. Yes, so this handles the input. Yeah, so this line, so we are looking at the square below the inverter. So if that square is empty, it's not going to affect. So for instance, so it now just, okay, let me show you this from scratch. This is the implementation specific thing, which probably might be done better, but yeah, so let's put an inverter in here. So now inverter is not activated, but if we put some wire in here, it gets activated. But if we erase this, it doesn't get deactivated, because it doesn't consider the empty square as the logical zero. So to make sure it is the logical zero, we need to put a wire there. And this is somewhat similar to, we just put a switch and make it like this. So yeah, now it drops. But yes, so now if I turn this like this, oh, sorry for this. Switch. So this is quite important, so I just want to make sure you pay attention to this. So I toggle the signal, and it toggles this one. But you might be wondering that having zero, like with a connected wire, which is not powered on, might be exactly the same. So if I just if I power down, it gets toggled. However, if I just erase this one, okay, so it doesn't affect, so I can still, it seems like no matter that this is not powered, so this is logical zero, and here it should be logical zero as well, but it doesn't work that way. So you need to make sure the wire is actually connected there. And in that case, so you either activate or deactivate. And this is very similar to how you can place torches in Minecraft. So in Minecraft, you need to make sure the torch is like on top of something. It probably works without that as well. But yeah, so that's how this works in this particular implementation. So to make sure that the input is equal to zero, you need to make sure that there is some element like wire. Probably light is supposed to be working exactly the same way. Yes, operate. I think light is going to be working. Yes, light works. So there is literally no difference between the green wires and the red lights. So they are the same programmatically. But if you don't have anything there, it's just not supposed to be working. But now, another thing is when we have our inverter like this, so we just give the logical zero, which powers it up. And now whatever connected to the inverter also gets powered up from the inverter, as if inverter was the power supply. This sounds weird from the electrical perspective, but that's how it works in Minecraft. Well, at very least, like conceptually. So this line is responsible for powering up whatever gets connected to the inverter. So direction width is the opposite to direction minus width. So this is direction minus width. This is direction plus width. Yes, like it's an inverter. It's hard to wrap your mind around because the direction when it like calls, well, just enough. It's well enough to explain that this line makes sure that, again, summarizing, so this line says the following: if right over in here in the input we have the logical zero, this would power up the inverter. Now this line says if we have the logical one in the input in here, in that case we power down our inverter. And this line ensures that whatever connected to inverter, like from here, copies the state of the inverter itself. So we just set this is powered variable, just like we do in case this line makes the powered inverter working exactly the same as the power switch or the powered button. So hopefully that makes sense. Okay, so we didn't yet implement the button on its own, and I'm not quite sure. So where is the button? The button. Oh, actually we did. So yes, actually we already did. So in here, when we return the rendered element, so when it comes to the button, what it does, so what onClick does, onClick toggles the powered bit, and then after 2 seconds, so this might be changed later, so probably we can make this constant, it just drops back to what? To the original state, so it literally just toggles back. So let's quickly check this as well. If we have the button like this, then we have a couple of wires, and then we have the inverter, and then something like this, and go to operate mode. So click, changes, and drops back. And again, click, changes, and goes back. While the switch is permanent, so switch does similar thing, but just permanent. Okay, so permanently, like holding this. Once we get it released, it just drops back. So hopefully that makes sense. The last thing we can do in here, let's do this to make this constant. So let's call it tick delay. Tick delay. And put it in here. So let's make it a variable, because later we're gonna be like maybe adding some elements to switch it. So we can say like tick delay. All right, and let's say toggle delay for button. No, let's say button delay. Let's make it 2000. So these values can be changed later if needed. So I call it button delay. Button delay. Okay. Okay, so let's test this one more time. And going for a switch, put an inverter in here. Okay. All right, and if we put the button and operate, it works automatically. Okay, guys, so one last thing, and to be honest, I have no idea how that happens, but since it's something that is somehow available in Minecraft as well. So here is the thing. So just to give you an idea, in, well, let's say timing, it's probably better to say frequency. So in this case, no, let's drop back to switch. So in this case, we have like kind of 2 steps. No, how many steps do we have again? 1, 2. Yes. 1, 2. So 2 steps. And if we have more than one wire element in here, so let's say we can have no matter how many, and we put a switch in here, and again, so just 1 and 2, and drop back again, 1, 2. However, if I just do not use this, and I put a switch in here, in this case it's just 1, 2, 3. See? 1, 2, 3. Again, 1, 2, 3. So there is an additional step being added. Well, most likely this can be treated as the bug or the wrong implementation, but I don't care. So I would rather emphasize that we can actually make use of it. And since, again, there is something similar in Minecraft anyway, so I've been showing you this in the very beginning of this video, but to give you an idea one more time. So if we have a simple generator with 3 we actually need one more like this with 3 inverters. So notice the speed, right? So this is probably, if I'm not mistaken, this is exactly how it works in Minecraft. And no, actually here I probably need to make it I'm not sure whether can't say for sure really, but anyway, so you just see like this might be treated as an indicator. So how often does it change its value? And as opposed to this, let's build another one. So like this. Okay, so this one goes faster because we have 2 squares. So hopefully that makes sense. So yeah, this is it. See you later and cheers.